mean by odds? Let's say that the probability of success of an event is 0.6. So what is the probability of failure? So it's 1 minus 0.6, or 1 minus probability of success, which is equal to 0.4. So we define odds of success equal to the probability of success by probability of failure. 0.6 by 0.4 equal to 1.5. So what is the probability of or the odds of failure? Odds of failure equal to the probability of failure divided by the probability of success. So it's the reciprocal of odds of success. 0.4 by 0.6 equal to 0.67. So that's how we define the odds of success and odds of failure. What I have done here is that for each probability ranging from 0.1 to 0.9, I have calculated what is the odds of success, and you can see in the graph it's increasing in nature. So it's monotonous in nature. As the probability goes up, it also goes up, right? It ranges from 0 to the positive plus infinity. Then let's learn what is log odds. Well, log odds is nothing but the logarithm of odds. If p is the probability of success and 1 minus p is the probability of failure, then we define log odd as log of p by 1 minus p, as you can see on the screen. Like odds, log odds also follow the monotonicity. That is, with increase in probability, the log odd values also increases. The log odds ranges from minus infinity to the plus infinity. You can see on the screen I have probability values ranging from 0.1 to 0.9 and the corresponding odds and log odds. Okay. What is the importance of log odds with regards to logistic regression? Well, it's very important. Why don't we just model for the probability directly? Why do we model the log odd of the probability? Well, as you know, probability ranges from 0 to 1. So it's a bounded value. So the upper bound is 1 and the lower bound is 0. It's very difficult to model such a variable which has an upper bound and lower bound. Bounded variables are not very suitable for modeling, especially if the variable is a dependent variable. Hence, we take the logarithmic transformation of the odd and then model. So it serves two purposes. One of the good thing for us is that log odd is not bounded. It ranges from negative infinity, minus infinity to plus infinity. Okay, and then it's a very simple transformation. It can be explained very easily. So these are the two reasons why we actually model log odds instead of the actual probability value in logistic regression. Well, to explain how to interpret the odds ratio, I have taken a very simple example here. Well, this is directly a model coming from one of my data set, wherein the dependent variable is admit. Whether a student is admitted to a graduate school or not. Okay, so if a student is admitted, the dependent variable takes 1, else it takes 0. So it's a binary variable. I have used logistic regression to model this variable. I have got one independent variable which is GRE score. Okay, my model looks like this: log of admitted by not admitted, just like p by 1 minus p, right, is equal to minus 2.9, which is the intercept, plus 0.00358 GRE score. So 0.00358 is my slope coefficient for GRE score. You can see that in the analysis of maximum likelihood estimate, this is directly taken from the SAS output. You can also see the odds ratio estimates for the independent variable. It's 1.004. So we are curious to know how odd ratio is interpreted and how is it related to the maximum likelihood estimates. Okay, so before I talk about the mathematical explanation, let me tell you that order ratio is nothing but the exponential of the maximum likelihood estimate. But how do we know that it's the exponential of maximum likelihood estimate? Okay, we will see why is that so. Let's assume that a student has a GRE score equal to 300. So what is the log or that particular student will get admitted to the graduate school? Well, put 300 in place of the variable GRE and calculate the log odds. Minus 2.9 plus 0.00358 into 300. Let's say that the GRE score increased by 1 unit. Now the GRE score is 301. So what is the log? Use the same equation, same logistic regression equation. In place of 300, you just put 301 this time. Okay. So what is the difference between the log odds when the GRE score increases by 1 unit? Well, you just subtract one from the other. We will subtract the second equation from the first, and it can be done very easily. So what is the difference? The difference in the log odds is nothing but 0.00358. So is this number familiar? Yes, it is. So what is 0.00358? This number is nothing but the slope coefficient of GRE. Okay, if you go back and see what is the slope coefficient or what is the estimate for GRE, it's the same number, 0.00358. So we could see that when there is a unit change in the independent variable, the corresponding change in the log odds is nothing but the estimate of that particular independent variable. All right. So what has it to do with log odds? Okay, let's see. Well, we see that we saw that how to how to interpret the log odds, right? So log odds is nothing but the change in log odds is nothing but the estimate itself. Let's transform this in terms of odds. In terms of odds, we just need to take the exponential of that. You know that the reverse transformation of logarithm is nothing but the exponential. if you take the exponential of the difference of logger, okay, you can see on the screen, you just have to take the exponential of 0.00358, okay, because that is the difference between the logger, which comes out to be 1.004. Okay, so what is 1.004? Let's go back and check if this figure is, this figure or this number appears in our output. Okay, let's see in the output where it appears. Well, 1.004 is nothing but the odd ratio estimate of GRE, right? So um, it's the exponential of the change in the odd ratio. Okay, so a odd ratio. Okay, sorry. It's the exponential of the change in the log odds. Okay, so odd ratio is nothing but the exponential of the change in, or the difference in the log odds. So how do we interpret it? How do we interpret the odd ratio? Well, an increase in 1 unit in the GRE score increases the odds of getting admission in the graduate school by 0.4%. Where does this 0.44 come from? Well, you can see 1.004. Okay, so the extra value, after the 1 is what is adding, is added to the chances of getting admitted to the graduate school. So whatever is there after this point, this point, and take just 1 away from it, like 1.004 is there, subtract 1 from there, so what remains is 0.004. Had it been 2.004, just subtract 1, it remains 1.004, right? So, and change it to percentage, change it to in terms of percentage. Okay, so 0.004 in percentage terms, it's 0.4%. So an increase in 1 unit in the GRE score increases the odds of getting admission in the graduate school by 0.4%. So that's how we interpret the odd ratio in a logistic regression. In this video, I'll talk about concordance or concordance index. They are essentially the same. I'll talk about how to compute concordance index in a data set. We will be using base SAS and proc SQL to do that. Let me show you the data set for which we want to compute concordance. My data set is output data. Let me take it to output data first. Okay, as you can see on the screen, I have a data set for 400 students. The first column is admit, whether a student is admitted to a graduate school or not. If it is admitted, then the variable takes 1, else it takes 0. So admit is my dependent variable for the model. I have got 3 independent variables: GRE, GPA and rank. GRE and GPA are continuous variable. Rank is a categorical variable and ordinal in nature. I have saved the output probability after building the model. So you can see the estimated probability here. If you click on this, you will see actual name of the column. The name of the column is spread underscore probability. And I have lower confidence limit. and then upper confidence limit for the estimated probability at 95% confidence level. So they are essentially the upper limit and lower limit of probability. I don't need the lower limit and upper limit. All I need here are two things: admit and estimated probability. Using these two variables, I can compute what is my concordance for this particular model. Of course, we compute we get concordance directly from the proc logistic. But to understand what concordance is all about, it is very important that we do it by ourselves. We need to write a code which will compute the concordance instead of SAS directly giving it to us. And we'll see there will be slight difference, but there is almost they are same. The only difference is because the way SAS counts it is slightly different than the actual formula or actual way of getting the concordance, and I'll tell you why the difference is later. Well, for the simplicity, I am taking only the first 100 observations. You can of course take the entire observations, but I want to keep it short, ensuring that it doesn't take much time to run. If you have time, you can take the entire data set. um, so I'm keeping only the top 100 data points, but remember, if you want to compute concordance, you have to take the entire data set. If you are computing for the entire data set, you have to keep the entire data set in the place. Now I'm subsetting the data set into two data sets. One is where admit equal to 1, and the other place is the other data is where admit is equal to 0. That means in the first data set out 1, I have students those who are admitted, okay, and in the out 0 I have students who are not admitted. So if I run these two things, okay, let me go to Explorer. Let's check the out data set first. So you can see only 100 data points are there. Okay, I have taken only 101. Let me go to out 1 and out 0. So let me go to out 1. So out 1 has only the admitted student. So 32 students are admitted out of the 100. So admit equal to 1. Okay, let me go to out 0. 68 students are not admitted, where admit equal to 0. Okay, now what I'll do is that I'll cross join them. I'll cross join. So how do we cross join two data sets? So we have out 0 and out 1, right? I'll do a cross join. So I'll use proc SQL for that. I'm creating a table. You can see in the syntax, and then I'm selecting admit from the admit 1 data set. Sorry. I'm selecting admit and from the admit 1 data, sorry, out 1 data set, and then admit from the out 0 data set, predicted probability from the out 1 and predicted probability from the out 0. I'm giving them different aliases just to understand it better. Okay, you can check the syntax again. Well, let me write it for you. I think it will be easier to understand. Proc SQL create table concordance as select a dot admit So A is my first table, out1 as admit1 and give it as 1, admit1. Then B dot admit. So B is the table, out0. I'm taking the same variable again and calling it as out0. A dot predicted probability, I'm calling it as predicted probability 1. Give comma B dot predicted probability, I'm calling it as predicted probability 0. Okay, then from out1 cross join out0. Right, so out1 is alias A, out0 is alias B. So table out1 is denoted as A, table out0 is denoted as B. Quit. Let me run this. Okay, so let me go to the concordance table. So you can see admit 1. So what essentially I am trying to do is that if you have like 32 ones and 68 zeros, when I am doing a cross join, how many observations you will have? 32 into 68. Okay, because for everyone you will have a 0, right? So that is a cross product of that. So that's why we have done a cross join. Estimated probability. So if you go to the actual column, in one case it will be predicted probability 1. That means predicted probability that is there with the the admit cases, where admit is equal to 1, and the second case is predicted probability is 0. That means predicted probability for the non-admit cases. Okay, so essentially in a nutshell, if I have to, if I need I am to summarize, you take the admit variable and estimated probability from the cases where admit equal to 1, and you take admit variable and estimated probability from the cases where you have admit equal to 0, or the non-admission cases, and then you do the cross product. Okay, so this is the data set, and from there we will define what we call it as concordance. So what is a concordance? If so, we have now pairs, right? 1 and 0. So you have like how many pairs? 2176 pairs. So pairs of 1 and 0. Okay. So if the predicted probability of 1 is greater than predicted probability of 0, you can see this condition. Pred of 1 is greater than pred of 0, then it's a concordant pair. Okay. If predicted probability 1 is less than predicted probability 0, then it's a discordant pair. Okay, and if they are same, I call it as a tied. Okay, or tied cases. Okay, so if it is a concordant pair, I am assigning a variable called concordance here equal to 1. If it is a discordant pair, okay, predicted probability of 1 is less than predicted probability of 0, I am calling it as concordance is equal to, I am assigning concordance is equal to 0. That means there is no concordance, it's a discordant pair. If it is tied, we call it as half concordance. Okay, so concordance is equal to 0.5 here. Okay, so that I am saving it in concordance 1. If you go to concordance 1, let us go to concordance 1. Okay, so you can see the concordance pair and the discordant pair. There will be very few cases where you have the tied cases. In fact, I don't think there will be any tie cases, but yeah, sometimes you will have tie cases as well. So this is a concordant pair. Why so? So if you compare your your predicted probability of 1 is greater than predicted probability of 0. Hence it is a concordant pair. If you go to the next one, same. Predicted probability of 1 is greater than predicted probability of 0. Hence again it's a concordant pair. If you go to this case where concordance is 0, the predicted probability of 1 is less than predicted probability of 0. Hence it's a discordant pair. Okay. You can do a prop to see how many concordance pair and how many discordant pairs are there. Do a prop data concordance is so there are 1566 concordant pair and 610 discordant pair. So the percentage concordance is 71.97 and percentage discordant is 28.03. Okay. Now once you have this concordance, the proportion, you can compute the concordance index in two ways. You can directly use proc means and it will give it to you. Else what you can do is that you can use the formula here. Okay, so what is this? Your C value is nothing but your concordance pair plus 0.5 into tied. Okay, so total number of concordant pair plus 0.5 into tied divided by total number of pairs. Okay, so see the formula again. Your C statistic is nothing but concordant pair plus 0.5 into the tied pairs divided by total number of pairs. So that's how you get your concordance index. If you want to directly compute it without using this formula, you can directly compute it by doing a proc means. So I am doing a proc means of, for the variable concordance. Remember the concordance is defined here. Okay, so if I do that, I'll directly get the concordance. When I'm taking the mean of the concordant variable, I'm getting it as 0.71966. Okay, so my concordance is 0.71966. I can take it to only 2 to 3 decimal, so it's around 72%. Okay, so that's how we compute concordance. Just to summarize, concordance is an important index. It lies between 0.5 to 1. 0.5 concordance of 0.5 is no good, and it's a very bad score in the sense that it doesn't help us doing the model has no predictive power, so to say. And concordance of 1 is a perfect model. So concordance basically lies between 0.5 to 1. What is concordance? Well, it is a probability that if you choose randomly one event and one non-event, the probability score for event is higher than probability score for the non-event. So the higher the concordance is, better is our model. And the objective of the analysis or the modeling exercise should be to improve your confidence as much as possible. You can get it directly from the proc logistic, uh, and if you want to if your software doesn't give you, you can directly use the algorithm or this small piece of code I have written directly to get your confidence.